Okay, I guess it's not going to yell at me. Cool. Okay, so I'm starting today, and for the next couple of weeks, we're going to be doing numerical linear algebra. And this is, I think that this is maybe one of the more like dry versions of the course. I have a couple of things I've added this year, I think, that deal with random matrix theory, which I think is pretty interesting. And from here forward, I probably won't spend as much time focusing on Python syntax. I'm just going to focus more on the algorithms. So I do think, but I would say if you're new to Python, it is worth practicing a little bit because some of this stuff, especially with like the deep lore of NumPy, if you haven't seen it before, it just takes some getting used to. And this stuff is going to be super useful because even though it seems very standalone, it's going to be somewhat useful for numerical integration. And this is going to come up actually quite a bit, even for introductory machine learning. So even though these algorithms, like most of the time, you don't need to know cold how to find an eigenvalue numerically, it's useful to know how it's done because that's useful for understanding why machine learning algorithms are the way that they are. And one of the homework two problems, the power method, is actually the kind of thing that does get asked in interviews. So it's worth knowing about that particular algorithm. Okay. So here's my notebook for today. Let me zoom in on this. Hopefully that's big enough. Okay. So I think that I've compressed this a little bit this year so we have more time to do ML. So I think that we're gonna spend maybe 1.5 lectures talking about how to invert large matrices. And we're gonna focus more on runtime than you might have when you saw this in like a linear algebra course. And then I'm going to spend probably maybe even 2.5 lectures on spectral methods, partly because this stuff is like pretty interesting and it's super relevant to machine learning. So that's the current plan. So we'll just do LU factorization. We won't do any of the fancier inverse stuff. Okay, so why in a physics context do we care so much about solving large linear equations, especially given that most physical systems are inherently nonlinear? The most obvious case, right, is that almost every PDE solving method comes down to breaking down your dynamical system into a super big matrix multiplication. As long as that matrix depends on time, that's a nonlinear system. But almost all methods you'll see in numerical integration involve linear algebra. And so it's useful to have at least some intuition for what the bottlenecks are when you're solving big PDEs. The other cases that comes up, the big one is optimization, which we'll talk a lot about at the end of this unit. But even intuitively, linear regression is like the core key machine learning algorithm, right? Like we motivate all machine learning just from solving linear best fit equations. And so sort of having intuition for why long skinny matrices are underdetermined and fat matrices are overdetermined, that can give us a lot of intuition behind, how some of these giant fancy models work. And perhaps more pointedly, something as simple as a deep neural network is just a series of matrix multiplications. So you can imagine that a lot of the intuition from these will inherit over to really fancy things. Okay, so what gives this sort of timeliness versus, taking a course like this in the 1990s? So, Moore's law for CPUs kind of came to a standstill. I think people still argue about that. But Moore's law is definitely still the case for GPUs. So right now, basically due to technological innovations, it's easier than ever to perform really, really large matrix multiplications. And people will disagree on this, but one argument for why deep learning is a thing now isn't so much that there were algorithmic developments, right? We've known about perceptrons since the 80s and even the 70s by some arguments. But what really happened is sometime around the late 2000s, it got really, really easy to use GPUs. And so all of a sudden people thought, let's start running these algorithms on GPUs. And all of a sudden, deep learning was born with the 2012 NeurIPS paper. So, GPUs have made linear algebra suddenly a lot more interesting. And it's suddenly all these really obscure algorithms from the 80s people are revisiting because they're relevant to optimizing on GPUs. And this graph is a little bit out of date. I think that GPU compute has actually exceeded CPU thresholds right now, but I wasn't able to find a new version yet. Okay, so we'll talk about spectral methods later, but right now we're going to focus on the really, really sort of common case where you're solving a linear system. And this is going to be matrix inversion. So I think everyone has probably seen this before, but just to give, some physical intuition, the kinds of problems where you see this come up are things like finding routes through flow networks, as well as problems where maybe you're trying to find stiffnesses of large composite materials. Those are two cases where you might have really, really large equations of the form AX equals B. So physically, for example, if this was an elasticity problem, X might be something like the position of every single one of the materials in a solid. A would be something like a coefficient of stiffnesses, and B would be something like the force, and this would give you something like Hooke's law in many dimensions or something. And so if we are given two of these variables and we want to find this one, we have to perform a matrix inversion, which is the whole question, is how difficult that's going to be when we go to super high dimensions. Okay, so unlike, low dimensional matrix inversion, there's a couple of things that you can imagine running into. The most obvious one is that if you have some super, super big matrix, like A is, I don't know, 1,000,000 by 1,000,000 rows and columns, you might not be able to fit the whole matrix in memory. So that's going to require some tricks to maybe get around that. And then also there's the case where maybe A is not actually square, so it technically doesn't have a well-defined inverse, but there might be ways to maybe approximate an inverse that's close enough under various circumstances. So those are two problems that you can run into, but the one I'm really going to focus on today more has to do with the properties of A itself, which is the case where A is almost a singular matrix, and we'll define what that means in a little bit. And I like this problem because it's an example where even if your problem is well posed by its structure, the wrong elements in that matrix can make this surprisingly hard, at least numerically. Okay, so I think all of us have sort of seen this before, so I don't want to linger on this because it's not as exciting. But a classic example where you might see a giant matrix inversion are the circuit solvers. So this is a really simple Ohm's law problem, right? You could imagine drawing this out and doing it like you do in an undergrad course. There are actually these really fancy solvers that people have developed that solve this when you have like thousands of resistors. And you can imagine that might come up if you're doing something like designing an integrated circuit, right? Where the resistivity is like the length of the connection between two pins or something. So these giant software packages where you basically place a bunch of objects on an integrated circuit, you're trying to optimize routing, but then you need to calculate stuff like the power dissipation, the voltage drop, and all that. And those packages are basically numerical linear algebra packages in disguise. So for this problem, I trust that given enough time and enough scratch paper, I could probably write down the equations that describe this. And it turns out that if you were to write Ohm's law for this system, it would look something like this. Okay, so the matrix form of Ohm's law relates a resistivity matrix, which is a square 3x3 matrix that maps this 3x1 vector to a 3x1 voltage vector. Okay. So if I want to invert this matrix, the first thing I'd want to do is say that I want to find my currents given some voltages. Usually in a circuit solver, you know where you're applying voltage because that's something you sort of solder onto your chip. But you want to find currents because that tells you whether you have sufficient current to power each one of your elements. So to solve this system, we need to take this R matrix, invert it to get I as a function of some matrix times B. So I can do that, I can do that using built-ins just by taking my coefficients, writing this big matrix. It's 3x3, so it has a well-defined inverse. I define my voltage vectors. That's a 3x1 NumPy array. And then I'm just going to use a built-in function here to compute the inverse matrix, multiply it by my voltage vector, and I get my currents. So here I'm not going to actually define this algorithm. I'm just going to use a built-in for this. But all I'm doing here is this is 3x1. This inverse is 3x3 because the original matrix is 3x3, and I get a 3x1 vector back out.
Is the at symbol like some like three?
Yeah, so this is I think Python specific because I think at is different in MATLAB, but at means matrix multiplication. But I could also do currents equals np.matmul, and I have to do the inverse. And there's even actually other ways to do this. So, for example, dot products are basically just matrix multiplications with a vector instead of a matrix. So you can also use dot. And then I will almost never use this because I think it's really pretentious. But there's actually in NumPy as well as in TensorFlow and PyTorch, the two big machine learning frameworks. There's actually support for Einstein notation. So you can actually specify which indices you're summing over. There's no way on earth that you'd want to do that for a circuit problem. But sometimes in machine learning, you're dealing with four-dimensional order 4 tensors. So you have 4 different dimensions as opposed to 2. usually something like batch, 2 dimensions, and index or something. And in cases like that, like you have, 4-dimensional tensor, so you need to manually bookkeep your indices. So in cases like that, you'll actually see people use, I guess, np.einsum, and you actually specify that I want to sum over the J index here because it's repeated. So yeah, I will try to never use this, but you'll definitely see this pop up when you're working with much, much higher order tensors.
Just ask like what is like element by element?
So element wise would just be that would just be voltage vector vector, and I would just do times voltage vector. So this would just do element wise. However, my voltage vector I think right now has shape array. Oh, oops. This is voltage. Oh, I need to run that. Okay, so it's shape 3. So that means that this product should give me element-wise product, and it did. But remember that if I do something weird like I do, I think transpose times voltage vector, and then I lift this with a dummy index, I might have this reversed. Then this will actually take an outer product because I've lifted it to a dimension. So it actually respects this whole contravariant covariant thing. If I decide to put in a dummy index to promote it to a 3x1. Yeah, I think so. And this is interesting because when I don't have that lift voltage vector, oh, this is I think a markdown cell. So voltage vector dot t is just going to give me the same thing back. But if I actually do the promotion to a full column vector, the t actually treats it implicitly as like a row vector when I take the transpose. So NumPy is cool because it basically can support like all of linear algebra, including like higher order operations. So it's nice to keep track of that. Okay. So that's, there's a lot of different ways to do matrix multiplication. You'll only use this when you're doing things that are not matrices, but are actually like rank 3 or order 3 tensors or something. Okay, so for all of the algorithms we're going to see, it's useful to just think of matrices as bundles of vectors, right? So I take sort of the canonical view that if I do a matrix vector multiplication, I'm taking a sum of a set of column vectors. That's my matrix with the weights set by my the vector I'm multiplying by. I like this convention because this is actually similar to something you see in machine learning, where you'd call this the key and this the values. So those of you who work on attention-based networks like transformers might have seen that key value notation before. So this column, we've all maybe seen this before, but it's nice to think of these as sort of like indices into the column space. And that could be a useful way of thinking about some of these algorithms. And one reason I like this sort of set where you think of a matrix as a bunch of vectors is as a very natural sort of interpretation where any square matrix defines a dynamical system. So if I think of, this is some square matrix, these are basically coefficients of each of these, and I mix them together with a linear combination. Then you get these really nice properties. For example, I can think of that matrix as specifying how much my other dynamical variables couple into the update of my current variable. And this gives rise to some intuition for a lot of the sort of like very dry theorems that you see in numerical linear algebra. So for example, the rank nullity theorem, which pops up a lot, you can think of that as sort of the fact that if I have a dynamical system that's only evolving in some subspace of its entire domain, there's no way to invert that subspace to get the full system. So you can basically convert the rank nullity theorem into a condition on the observability of really complex dynamical systems. So sometimes, this isn't the most profound statement, but it is useful to say that anytime I have a square matrix, think about what it would be if that defined a dynamical system, because that can give you some nice intuition for what some of these linear algebra theorems like rank nullity will impose on what that system can do. But it really only works for square matrices because otherwise you change dimensionality when I do the matrix multiplication. Okay, so the first big thing I want to talk about that maybe isn't covered as much in linear algebra is how difficult it actually is for your computer to perform matrix inversion. So we know that the inverse of a matrix is the matrix that when multiplied by the original matrix will give me the identity. And we can kind of get some intuition for what this runtime is going to be just by thinking about limiting cases. So one example of a limiting case would be the case where I have it's an n by n matrix, but A is a purely diagonal matrix. In the case where it's a diagonal matrix, and the diagonal elements don't have to be one, they can be any scalar you want. In that case, we know off the top of our heads that the inverse of that matrix is just 1 over each of the diagonal elements, right? And you could prove that to yourself by actually solving out the matrix multiplication. And that's nice because you can guess from that if I'm given some matrix, it's n by n, and I'm asked, find me the inverse of that matrix. If I know in advance that the matrix is diagonal, I can just touch every diagonal element once, right? I just have to flip each one upside down. So I would expect naively that inverting a diagonal matrix should be runtime of order n, because an n by n matrix has n diagonal elements. So that maybe gives us a lower bound on what the time complexity of matrix inversion should be, which is that in this one special case where I can only touch the diagonal, it should be runtime n. Okay, and here I've just done sort of a poor man's matrix inversion where I've defined an identity matrix, I've populated with random diagonal elements, and then I manually find the identity matrix, or I manually invert the matrix, and lo and behold, matrix product gives me the identity matrix, as I would expect to see. Okay, so that's best case scenario, we get runtime of order n. So then the next best thing that we could expect to get would be the case where this is an upper triangular matrix. So this would be a case, I didn't print one out here, but maybe I could add one, where all of the elements above the diagonal are greater than or not equal to 0, but everything below the diagonal is equal to 0. So it looks like a triangle or something. So to figure out what the runtime would be here, it's useful to go back to thinking about matrices as defining algebraic equations. Because if I have some algebraic equation that has the form where I have, a bunch of zeros in the bottom, then I have that equal to something, I have to do one operation to solve that bottom equation. I then substitute it into my next equation. I go up, I only have to solve once. And so in fact, in order to solve an upper triangular matrix inverse, I only have to touch each of these upper elements. And so the question is, how many are there? And it's basically 1/2 n squared is the total number of elements I have to touch. So that means that if I have an upper triangular matrix, I can't get away with order n operations, but I can get pretty close and do order n squared. Because in the specific case where I have an upper triangular matrix, that corresponds to the case where I can do this nice algebraic solve where I solve my bottom equation, substitute it into the next simplest one, substitute that into the next simplest one, just go up the hierarchy. So inverting a diagonal matrix is of order n, and inverting an upper triangular matrix is of order n squared, because I only have to touch each of the elements once, but there's n squared, or a number proportional to n squared of those elements. Okay, so then the question is, okay, so that's fine, but how often in the real world do we actually encounter triangular matrices? Based off of that, can we suss out what the time complexity of full n by n matrix inversion is going to be? And this is where it gets into I think the really boring stuff in linear algebra, right? Because at least when I took linear algebra, we spent, I don't know, it felt like weeks very manually solving large systems of matrices using Gauss-Jordan elimination, right? So recall that's this really fun exercise where you pick a row, multiply it by a scalar, subtract it from another row, you get something new. You take that row, and you basically one by one try to build an upper triangular matrix. And then once you have an upper triangular matrix, then you solve and you're basically done. So we know that once I get to this step where I have a triangular matrix, this I should have moved over. Once I get to the point where it's triangular, I know I have n squared operations. So if I can put this in an upper triangular form, I know that it's n squared to invert. So the extra runtime I'm going to get is basically how many operations I have to perform to put a generic matrix into upper triangular form. And it turns out that is a number of order n. So the full inversion of a square matrix is n cubed, which I think is confusing because you'd think it would be n squared because there's n squared elements, but that extra factor of n comes from basically the Gauss-Jordan necessary to get your matrix to upper triangular form. Then you do n squared operations. So the runtime of full matrix inversion is n cubed, and that's an extremely useful scaling to know, because a lot of numerical integration schemes, it's useful to know how costly it's going to be to invert a matrix. And just generally in a lot of machine learning things, you're doing matrix multiplications all the time. So it's worth knowing how much it's going to cost. Yeah.
Isn't there any way to see why this order n is because I would have thought below the line we have n squared elements.
Yeah.
N squared elements. So how is this order n?
Yeah, I was trying to think of a good example of this before class. Because you think that eliminating all of the lower diagonal elements would take n squared, so you get n to the fourth. I'm wondering if it's because you don't like, so every Gauss-Jordan step, I basically turn one thing into a zero, but I think I have some structuring when I do that, right? So it's not like I'm sort of uniform the space of operations I can do on the rows. Like I think that once I create a zero here, I'm constraining my choices for future moves. And so somehow I don't actually have to do a full n squared possible operations because like once I put a zero there, there's fewer options now. So I think that there's structure in the solve of the lower that causes there to be fewer operations. But again, that's sort of hand wavy. I don't have better intuition for that. But there has to be some constraint, I think, on the set of steps. But another way to think of it, though, is you can actually write a Gauss-Jordan like row echelon form elimination. You can actually write that as a matrix multiplication itself. In matrix multiplication, good thing to know is that n by n matrix times an n by n matrix is n cubed operations. So the n cubed pops up like everywhere when you have square matrices. So it's just worth knowing about that. Yeah, and one other thing I'll just say, right? So
Is that also what you see with the runtime and as you like scale up the matrices?
yeah, so this is the runtime because this is number of like I count one operation as a single product or sum between two scalars. So any binary operation I count as that. And so yeah, that's why I'd say that this is the runtime scaling. Yeah. And one thing I'll just mention, right, is that if we know that this is an n squared or an n cubed process, we can back out what matrix vector multiplication would be, which is that I only have to do one product across the column space if this is a matrix vector. So matrix vector multiplication is n squared. So these are some good things to have in mind, which is n by n matrix times n by 1 vector, n squared, n by n matrix times n by n matrix, n cubed. And it's only in really special cases that you can speed that up because maybe you have structure in your matrix. And a lot of methods for accelerating numerical linear algebra involve seeing if you have some structure in your matrix that you can exploit to do fewer than the full n cubed. That's what we saw in the Fourier transform example. Okay. So one of the things that comes up, not so much in like real linear algebra courses, which are often a bunch of proofs, but which is super, super important for doing this on the computer, is that because we have these numbers in this matrix specified by floats, which have finite precision on a computer with a finite number of transistors, we need to think very carefully about the elements of the matrices that we're multiplying in order to avoid having issues occur due to accumulation of numerical errors. So we're going to introduce a quantity called the condition number, which is going to be a single scalar, which you can think of as like an order parameter for how hard a matrix is going to be to invert numerically. So the formal definition of the condition number is going to be the Frobenius norm of a matrix is just the p norm of its elements. So usually we're just going to use p equals 2 because it's a little bit pretentious not to do that. So this is just going to be the sum of the square of every element in a square matrix. And so like I take this matrix, I take the sum of all of these elements, and that gives me that matrix, the matrix's norm. And then I take the square root because it's a norm. So the condition number is equal to a matrix's norm or matrices norm multiplied by the norm of its own inverse. And this ends up being a very loose measure of how difficult that matrix is going to be to invert. So that's how I write an equation form. If I write that out in sort of NumPy form, it just looks like this. So I take the absolute value, I raise it to p, and then take 1 over p. But usually I'm just going to have p equals 2. So I set that as a keyword argument. And then I'm just going to use NumPy built-ins for now. We'll talk more about how to actually implement inversion later. But for now, we're just going to assume that this gives me the inverse matrix. And I would calculate this, multiplied by that, and that should give me this number c. So the condition number is a scalar that tells me something about how difficult a matrix should be to invert. Okay, so the reason that the condition number is a useful quantity, let me get this in my memory. Cool. Is that it basically ends up being a measure of how close the columns of a matrix are to being parallel to each other. So what I'm going to do in this example is I'm going to build a four-dimensional vector. So this is just a random four-dimensional vector. All the elements are probably non-zero. And what I'm going to do is I'm going to build a 4x4 matrix out of that 4x4 vector where every column is that vector plus a random number. And I'm going to vary the amplitude of that random number. So what this demo is going to do is when I have the noise as some super, super tiny number, this is almost going to be a matrix that has four parallel column vectors, right? Because if I have noise of an amplitude of 0, then it's just A1, 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 A1. And so as I increase my noise level, I'm going to have a lot more components that are off the direction of A1. So the intuition here is that basically I start from the case where the rows are almost parallel vectors, and I'm going to gradually make them less parallel to each other. Okay, so when I run that, and I think I can hopefully run that in memory. Yeah, cool.
Like, what does it mean to be all parallel?
Oh, I maybe I should just draw like a diagram. He always puts the eraser.
You mean like equal in this context?
Yeah, so if I write my matrix I'm inverting as, do we not have white chalk today? Huh. Oh, next. Budget cuts or something. Okay. So my degenerate case is when I have like so V1 is going to be my is an element of R4, so this is going to be my 4 vector. So the degenerate case is the case where all of these are V1. And this matrix, right, is an element of R by the 4 by 4. So this is going to be the degenerate case because all of the rows or all of the columns point in the same direction. They're all the same vector. So that's going to be where I start. Then I'm going to add a really tiny random vector. So I'm going to say that epsilon is an element of R the 4th. So I'm going to add a random vector to each of these. And as I increase the amount of this, it's going to make these vectors be less parallel to each other or less of the same vector. So I'm basically just titrating how different these vectors are from each other is what I'm going to do by adding a random vector of varying amplitude. Okay, so if I do that, so one case that I didn't do is if I set noise equal to 0, this would throw an error because the condition number would be infinity. So I actually start noise out as just 10 e to the minus 5, so some super tiny number. So in that case, I get a condition number that's 10 to the 7, so that seems pretty bad. And then as I increase the noise level, the noise eventually drowns out the original elements of that. So I just end up with basically 4 randomly drawn vectors here because the amplitude of A matters a lot less than this. And so as a result, I basically have 4 random vectors, and it turns out that most of the time those aren't parallel to each other. And so my condition number drops really quickly until eventually I get to having a condition number that's super, super small or relatively small for this problem. So condition, and notice that this is a logarithmic scale here. So condition number has sort of a logarithmic range. It can go as high as infinity, but basically it tells you how parallel the columns of your matrix are is what you should think of it as. And we're going to argue that having very parallel columns is going to make your matrix harder to invert. So you want this to be as small as
Why
possible.
is that?
We'll see an example of that in a second. Yeah. Okay, so that's condition number, but just think of it as if it's big, that's bad. And if it's big, that suggests that at least 2 of your column vectors are close to parallel to each other. That's basically what it's telling us. Okay, I think I ran that. Okay, so here's another way of looking at that. So here I'm going to define 2 vectors. Let me make sure I have all the code imported to get this to work. Okay, I think that this should be working. Okay, yeah, cool. Okay, so what I'm going to do in this example, right, is I'm going to define I'm going to find two column vectors and I'm going to manually add this epsilon term to it. So I'm basically going to do what I did here, but we're just going to we're actually going to physically draw the two column vectors to see what happens to the condition number. And I'm going to try to use these sliders, which sometimes they work and sometimes they don't. So my two column vectors in my matrix, when they're nearly parallel, my condition number is super big. And then oh, did I break that? Oh, I totally broke it. Let me try to rerun that. I think I broke my thing when I re-imported my notebook. Oh man, that sucks. Let's do this.
That's ChatGPT to fix it.
Yeah, I think oh, okay. It just has a really nonlinear response. I see. Okay, so what I'm doing here is my column vector is 1, 1, and my other vector is 1, 1 plus epsilon. And then then this matrix, which is a 2 by 2 matrix, I'm going to compute the condition number as I increase this shift off of the parallel case. So again, this matrix, the matrix that is just 1, 1, 1, 1, that should have a condition number of infinity because it's two column vectors pointing in the 1, 1 direction along the 45-degree line. So it's degenerate, the matrix isn't fully ranked. And then by adding this epsilon term, I'm basically going to make sure that this second element of that second vector is different than 1, 1. So this basically helps the matrix be less, have two column vectors that don't point in the same direction. So I'm just going to increase the value of epsilon. And it turns out it has a super nonlinear response. So I'm going to slide this vector and gradually add that epsilon. It's going to get bigger and bigger. And then out here, the condition number starts to drop, and you can see that that's where you see that those two column vectors are no longer parallel. So the condition number really tells you something about the vector space that your matrix defines, that the columns of your matrix define. Okay. So why do I care about whether a matrix has a big or a small condition number? So the most obvious case, right, is that if I have a condition number of infinity, that means I have two parallel column vectors. We know from linear algebra that a matrix, even if it's a 4 by 4 square matrix, if it has two columns that are identical, it's non-invertible. So an infinite condition number is super bad because you can't solve your problem. In practice, that might mean that you have something like a repeated data point, right? So you have sort of redundant data, so your problem is underdetermined. Or it might mean that you have, deficient rank in your problem in some other way. So repeated data points are bad, repeated features are bad. Basically, having a repeated column in a matrix, usually that's not something you want. And that's signaled by an infinite condition number. What's interesting about the condition number is it actually softens that because it says that even if I don't have two repeated vectors, if I have two vectors that are close to being repeated, so they're nearly parallel, that still is going to cause problems for me, at least numerically. So here what I'm going to do is I'm going to generate a giant 500 by 500 matrix, and I'm just going to compute the condition number of that matrix. Then I'm going to generate another 500 by 500 matrix that I'm going to deliberately make be really close to ill-conditioned. So I'm going to make sure that a couple of columns of that matrix are very similar to each other. So these are both 500 by 500 matrices. Neither one of them is actually singular, but the second matrix is going to be closer to singular. It's going to have vectors in its column space that are close to each other. So when I do that, I'm going to just perform a basic linear solve. I'm not going to actually write the algorithms for this, but we're just going to do that matrix inverse and solve that equation. When I run that, NumPy takes a very small amount longer to solve the equation with the ill-conditioned matrix. And this is subtle here because I didn't want to run something that was going to like crush my computer. But as this gets bigger and bigger, like if I did 5,000 by 5,000, this timing difference would really start to get out of hand. And so this is interesting, right? Because like if I was given an actually singular matrix where everything was the same, I would never solve this problem. But the conditions number says that even if this is just some big number, right? It's, I guess, 10 to the 18 here, I will pay a timing penalty for that, just because of the fact that I have two very similar columns. And this is, I think, kind of cool. It's kind of like an order parameter for a matrix that tells you the behavior of this sort of like operation. And it's an example of how like sort of this mathematical property of the column space can actually manifest in the hard runtime of numerical algorithms. And I just mentioned that, the NumPy implementation of matrix inversion is presumably as efficient as you're going to get, and it still notices this difference here. So the condition number is super important to keep track of if you're working with big matrices. And I'll just mention those of you who work with neural networks, there's a lot of lore regarding the condition number of weight matrices, which are the large matrix multiplications you perform in deep neural networks. Okay. And then one last example I'll show in the condition number because I think it's kind of cool. I'm feeling like gambling, so maybe I'll try to rerun this and see if I break it. But just because I'm scared, I'm gonna do it in a separate cell. Oh, okay, it worked. Great. Okay, so what I'm going to do here is I'm going to take this dynamical systems view of matrix multiplication. What I'm going to do is I'm going to define an initial condition, and then I'm going to define some other initial condition that's very close to it. So this is going to be 2x1 vectors that are going to be, some initial point in a 2D plane. I'm then going to define an ill-conditioned matrix and a well-conditioned matrix, and I'm just going to apply those matrices a ton of times to my initial conditions. I'm then going to compute how far apart my initial conditions got over time. So the rate at which two initial conditions move apart from each other under the action of an ill-conditioned matrix versus a well-conditioned matrix. So when I do that, I see something kind of interesting, which is that under repeated applications of an ill-conditioned matrix, 2 points actually move apart at a slower rate than under repeated applications of a well-conditioned matrix. So in other words, the fact that I have a degeneracy in my column space, or at least close to a degeneracy, actually causes objects subject to the dynamics defined by that matrix to sort of disperse at a lower rate. And your intuition here is that because I have a close to repeated column space, my problem effectively has a lower dimensionality. And so as a result, I'm moving in fewer dimensions, so my dispersion grows more slowly. So the condition number almost can be thought of as specifying something like the dimensionality of the dynamical system associated with a matrix, where having a really big condition number means you have two very similar columns to each other, which somehow means that you don't sort of disperse as quickly, or two trajectories don't move as quickly apart through the space. So there's an interpretation of the condition number in terms of like the dimensionality of a dynamical system, which I think is a non-traditional way of looking at it. Yeah, what's up?
I guess it's a bit dimensional reduction approach. And say if you're building an NL model and you have two very close like column vectors, you might be just like delete one.
Yeah, in fact, that's like a big thing in logistic regression. People always talk about the collinearity problem, which is quite literally when you have two data points that one is just an affine transformation of the other, or not even affine, like a scalar multiple of another. And so if you have both in your model when you fit it, usually your linear regression will either overfit or it'll approach like some really weird solution. And so you should just delete one of those points, basically, is the recommended practice. It's deleting data, which is kind of funny. But yeah, it really is due to the idea that condition number implicitly defines dimensionality. Okay. So then the one last thing I wanted to do, just because this gets into sort of deeper issues that not just come up in numerical recipes, but which is like everyone's favorite thing to talk about in machine learning, is that we mentioned that high condition numbers are generally harder to work with. But unfortunately for us, if I generate random matrices, as I increase the dimensionality of those random matrices, my condition number actually grows. So this is a real bummer, right? Because it tells us that regardless of my compute resources available, problems get harder to invert intrinsically as I increase my dimensionality. So that means that as I get to super, and fortunately, this is obviously a sublinear trend, right? It's a semi-logarithmic, it's not quite. But it doesn't actually saturate. So as I get bigger and bigger matrix multiplications, I actually have a harder problem to solve. And that's not just due to, me having a bad computer or something. This is a fundamental structure of larger matrix multiplications, so that they are harder problems because you're much more likely to have two columns become collinear or nearly collinear.
Going back to the square root.
I'd have to look up what this scaling is. I remember it wasn't something really elegant that I could understand. Yeah, I guess I could try doing a log plot and see what I get maybe. Okay, so problems get harder as you go to higher dimensions, and people throw this term around to describe everything these days, but that's one way of describing the curse of dimensionality, is that you get punished for moving to higher dimensions. Okay. Yeah, what's it?
Should this be for any like ensemble of matrices, random matrices, or because some examples of random matrices, they have level like, they have eigenvalues which are very far apart, so their condition of machine will be.
I think you're right. I think it's for I think I need to say zero-centered random so that each element has a zero center. And I think as long as it has a well-defined variance, so maybe not the T distribution, but like a Gaussian or a Lorentzian distribution, I think all of those this still holds. As long as that second moment is well defined. And the hint there is like, dot products give you squared terms. That's why the second moment would come into that derivation. Yeah. Okay, so then the last thing I wanted to mention, yeah, we'll skip concentration and measure. Is I came up, I think, with a little bit of intuition for why it might be the case that higher dimensional matrices are harder to invert. And the idea is that I have a very high condition number if any two of my columns are close to being parallel. So as I sample vectors from higher and higher dimensional distributions, the odds that I get unlucky and at least two are parallel increase actually exponentially. And so you can actually derive the scaling for the probability that you have two very close to parallel columns, basically by counting out as I sample n random variables and I go to n samples from the distribution, what are the odds that two of them are close to each other? I did this using basically sort of the birthday paradox, this famous result from about the binomial distribution. But basically the idea is that if I have one vector, I don't have to worry about it. If I sample another vector in high dimensions, it's pretty likely that vector won't have any elements that won't be very close to my previous vector. But if I sample n of those, the odds that at least two are close grow very, very quickly. And so I get, even though I'm in high dimensions, the odds that I sort of go out and find another one that's close to my first one increase very quickly. So you can sort of prove using Stirling's approximation why this is the case. But importantly, it means that the cursive dimensionality isn't a computer specific thing. It's really sort of a fundamental property of high dimensional matrix multiplication. Okay. Then one last thing, and this is kind of related to the cursive dimensionality, but it's just kind of fun. While it's true that my matrix is more likely to be ill-conditioned as I increase dimensionality, it turns out that if I just think about the columns themselves, as I go to very high dimensions, two randomly sampled vectors are very, very likely to be orthogonal, not collinear. So this is called measure concentration, and it's one of these things that is very unique about high dimensional geometry. So here what I'm going to do is I'm going to sweep n, so dimensionality of my problem, and I'm just going to pick two random vectors. Again, I have a center at 0 and a variance of 1. And I'm just going to compute the angle between those vectors, again, randomly sampled as I increase n. And just because I want to have good statistics, I'm going to average over 400 replicates for each value of n. So when I do that, what I end up finding is that as I go to very high dimensions, the average angle between two randomly sampled vectors closes in really close to pi over 2. Right, so two randomly sampled vectors in high dimensions are almost always orthogonal. And this is a super weird property of high dimensional geometry. It certainly is not true in 3 dimensions, but it suggests that when you're working in high dimensions, right, if I have a data point, I have another data point, the inner product is most likely going to be 0, which is very unintuitive and, it's worth thinking about. And this is the other form of the cursive dimensionality that you'll hear people talk about sometimes. Okay, I'll go ahead and wrap up there. Thanks.